Alright, in the last video we went through and we walked through the truss members. So right now as it stands, we have 4 truss members accounted for on this truss that we have for number 5 on activity 216. So as we take a look, we've analyzed joint A and we've analyzed joint C to go through and solve for, through using those joints we're able to solve for 2 truss members each time. And right now we have 3 truss members left. And in order to go through and to start looking at what would I probably go through and solve for next, or what joint to use to solve for, I want to pick a joint that has the least amount going on with it. So right now, B has 2 vectors coming off of it. I really want to stay away from that because that's going to be a lot of work to do. E could be a possibility, and even with the support reactions, it just has the 1 vector pulling down and to the left. But I think the one I'm going to focus on here is going to be joint D. And joint D, I'm going to go and I'm going to draw a free body diagram for the joint in the little bit of space I have left at the bottom. We have a truss member that's pulling up, which is leading up to joint E. We have another truss member that is going to be pulling on the joint over to the left to go over to B. And then we do have the reaction from the roller that is pushing on, which is RDX, that is going to be pushing on the joint as well. And RDX is going to have 1,500 pounds of force, as we solved for back in the steps that we had from 1, 2, and 3, and lastly 4. Okay, so here, as I take a look, these are all the forces acting on truss joint D. And now I can go ahead and start looking at what are the forces that I have left to solve for. Sum of the forces in the y direction add up to equal 0. I only have one y direction force, which would be DE, meaning that truss member is not carrying any force or having to support anything. So DE is equal to 0. And then now, sum of the forces in the x direction. I've got 2 x direction forces acting here. So they are both acting to the left. Again, we flipped that x-axis direction. So we have dB acting to the left, which is going to make it positive, plus RDX. And when I add those together, those are going to equal 0. So dB plus 1,500 pounds is equal to 0. And then in order to get dB by itself, I'm going to subtract by 1,500 pounds on each side to make that happen. So dB is going to be equal to a negative 1,500 pounds, meaning that this truss member is in compression. And I'm going to go ahead and take these 2 values and update my free body diagram. So up here on the diagram, below 1,500 pounds, label in parentheses C for compression, DE, 0 pounds. Alright, now I've got one last truss member to solve for. So the crossbar here, which is going to be between joints E and B, and actually I'm going to start to look at, well, what joint do I have left to analyze? Again, I want to stay away from B. It has 2 vectors here. I could use it, but I have to do a lot more work to solve. I think I'm going to move to joint E. I just have the 1 vector, and the other forces are acting in a straight line X or Y direction. So I'm going to go ahead, I'm going to have to move to another sheet here to go through and to make this work. And I'm going to draw joint E. So here, joint E's free body diagram. I have the support reaction REY. I have REX coming off to the right. I have a truss member pulling on the joint over to letter C. And I have another one pulling down to D. And then I have another one pulling down at an angle down to B. So in this for joint E, we do have a force vector we need to break down. I'm going to call this vector EB. And I'm going to go ahead and redraw the vector and split this into its X and Y components. So in order to do so, I'm going to go over to the left along the x-axis, and then I'm going to go down in the y direction to meet the end of the arrowhead. And I've got 45 degrees there on the angle. So the x component, EBX, y component, EBY. This one, however, I'm going to kind of analyze. I only need one truss member. And when I start to look at my truss members, I'm also going to label what are my forces, the magnitudes of my forces that I have to deal with. So as you can tell, one of the things that we have is, I think I'm going to focus on just the y direction, because this DE truss member has 0 pounds, which is going to help me eliminate one truss member that I don't, or one truss force that I don't need to account for. So it's going to be a little bit easier to do that way. And so I'm going to go ahead and just deal with EBY. So again, I'm going to focus using y direction forces. This is the opposite side of the triangle, meaning we're going to use sine. Sine is opposite over hypotenuse. And when I plug in what I know, sine of 45 degrees is equal to EBY over EB. And then I'm going to solve for in terms of EBY. So all I got to do is multiply by EB on each side. And that's going to be EBY is equal to the sine of 45 times EB. Okay, now I can go through and take a look at, well, what are all the sum of the forces in the y direction? And they add up to equal 0. Here I have REY acting upward. I have, I'm going to call this DE. So I do plus a negative DE. Since that's acting downward, that's kind of a common notation we used in the last joint. And then the only thing I have is I need a negative EBY. So looking at my vector moving downward. And when I add those together, they should add up to equal 0. So substitution, REY was 1,000 pounds. My DE was 0, so I could pretty much kind of write that one out. And then plus a negative sine of 45 times EB, and that's going to be equal to 0. So rearranging the equation, I'm going to subtract 1,000 pounds from each side to balance. So I've got the negative sine of 45 times EB is equal to a negative 1,000 pounds. And in order to get EB by itself, I'm going to divide by the negative sine of 45, which is in turn going to make this answer positive. So utilizing my calculator, 1,000 divided by the sine of 45 is going to give me 1,414. Again, our precision is just to the tenths place, 0.2 pounds. And this is in tension. So, update my free body diagram. This is the truss member. (1,414.2) in tension. So this completes our truss calculation for number 5 on activity 216. And what you'll see when you come back to school, or when you're able to get to it, is you can actually check these in MD Solids using the trusses module, and actually check the answers to make sure that we've got the right solutions to the truss problems.